Hello and welcome in our demonstration of Testwell CTC++ test coverage analyzer from VerifySoft. Testwell CTC++ test coverage analyzer for C, C++, C# and Java is a powerful and easy to use code test coverage tool, which shows the parts of the code which has been executed and then tested. Testwell CTC++ can be used on host for native projects. Please refer to our other video describing our integration within the Microsoft Visual Studio IDE for more information. If you look for an efficient and easy-to-use solution for your IT projects, Testwell CTC++ is your best choice. But today, we will see how it can be used for measuring code coverage in embedded targets and microcontrollers. Its main benefits are very low instrumentation overhead, performs code coverage in all targets. It works even with smaller targets and microcontrollers, and works with all compilers and cross-compilers. We'll see how your code can be instrumented for analyzing its test coverage from within an IDE, such as Embedded Workbench from IR. Just take the regular C and header files in order to compile and link, but here in the process we have the instrumentation phase, and this is done automatically by the integration within the IDE. All gray-blue parts are used by our integration to generate the simul file, and what you just saw, it's to generate a data file from the target in order to produce the report. So today we'll demonstrate a project which is based on the same example we saw with the first video with IR Embedded Workbench IDE. The main difference is that this demonstration was based on a simulator mode, while today we'll use a real hardware target for running the application and to get the coverage data. So this evaluation board from Atmel is explained mini-board, and the processor on the microcontroller is an ATmega 328P, which is an 8-bit microcontroller from the AVR series. And we'll use the IR Embedded Workbench IDE, which is able to debug this board in a very efficient way, and also because we have a very good integration with this IR Embedded Workbench IDE. Okay, let's focus now on how we can save the data from the coverage analysis running on the target back to the host. So typically we are using the bitcov options because your target doesn't have any file system running on it. For this situation, we are using bitcov, which doesn't need to have any runtime library installed, so it's minimized the overhead impact on the global memory, as we only have to add a CTC array to our application in order to be able to collect the coverage data and later on to be able to generate a report. So this is how it works. In other words, we just talked previously about the mod.zip file and the mod.dat file, which are the classical files that the report generator is expecting. So while running on a target, this is a different mechanism where you want to have a mod.tox file which is generated by the instrumentation. So it's a kind of preliminary mod.dat file, but it needs more information from the analysis running on the target. Once you run your test, you will get from your target, and this is the first part of the demonstration, to save the CTC array values on the disk by using a save command from the debugger to save this in a mod.dat file, which is typically either a binary file, S format, S record format from Motorola or Intel HEX, which are well known for flashing or programming memories for embedded applications. So once you have this data saved here, you are able to translate this binary or proprietary format to something which is readable by CTC. It will be textual information. So we call this file model.txt, and then we will write an utility which is called CTC2dat that will convert the textual informations back to the mon.dat, and then we will be able to use the classical report generation for CTC. So let's start the IR embedded workbench IDE, and just a few words about our project. This example is the prime example, where the goal is to compute if a number that we will enter is a prime number or not. So for this, on this target, you have a USB channel which is used for both debugging through a JTAG feature, the software running on the target, and a virtual port, which is a serial interface. And for this, we have a program here able to be used as a console to enter and to receive messages from this virtual serial port running on the target. So here in this IR IDE, we basically add two menus. The first one is to control how CTC is used, so it could be on or off. So it's without exiting from the IDE, you can select if you're using instrumented code or not. The level of coverage you want to apply to the analysis, and the way the data from the code analysis is downloaded to the target. So it could be host target, which means that you will have your own functions to save the data on the target using the hardware you want. Or the most efficient way, if you have an access through JTAG like today to the target directly, is to use bitcov. Bitcov is simply storing all counters values to this global variable. So if the debugger is able to save the content in binary somewhere on the disk, and most of them are able to do that, then it would be very easy to get this data. You don't have to write anything on your own. Just tell CTC++ bitcov add-on that you want to use bitcov, and it will take care of all steps. Here you can also, for instance, select the files you want to take into account. Here, for instance, I don't want to have the initialization part of the board. I just want to focus on the application. So this is how you can select which files you want to add instrumentation or not. You can also clean the files which are generated by CTC++ add-on, and this is a different menu from the one you have in the IDE to clear or to clean all object files generated by the compile and link process. So this is the first menu. For the second menu, we'll be able later on to generate a report, and the report will be generated using HTML, XML, or textual format, and again you will select the coverage levels you want to achieve. But before to do that, I need to explain furthermore the difference with the previous video you may have seen. And this is just here in this menu. You can select the debugger you want to use, and for this board, JTAG ICE3 is the one we need to use. Previously we used a simulator. So now that we have chosen the way to communicate with the board and the way we want to have the coverage data, we are ready to compile, link, and to download everything on the target. So this is a single step process, just a single key here, and the tool will do everything for you in the background. compile link with the instrumentation done, and then downloading the code, the binary on the target here, and such a way you will be able to run it and to debug it on your target. So now I have a new toolbar, and from this toolbar I can reset the target, make some stepping, and simply execute the instrumented application. So let's do it. And now in my console I should have some welcome message and the application which is running. So basically I want to check if the number is a prime or not, so I will start with 5. Okay, 5 is a prime, good. Now I will try with 9. Okay, 9 is not a prime. Fair enough, maybe for this testing. So I will exit from my program by typing 0. So I'm done here for my test. So the next step now to do is to save the binary content of my CTC array global variable to the disk, and I will run my macro for that. So here I am now the file, and I can generate reports. This is what I'm going to do now. HTML, MCDC, and this is using the default internet browser. Okay, so now what I can see here is I have been good at checking the this function. This function not too bad, but this one is roughly half of the test for MCDC, and for statement it's a little bit better. And here, so the percentage is a test effectiveness ratio. So all those numbers need to be increased. So the tool is helping you actually to do that. So what I can do now is just have a look here, and for instance I can focus on the first pair of test vectors, and you can see that it consists of number 1 and number 4, and number 4a has been executed once. So, but the first one has not been executed yet. So if I want to have this test successful, I need to enter true for the first one, don't care here, don't care here. So I will focus on here. So that means I need to just input 1 as a value and see what's happened. Okay, so exit from here, reset the target, go again, and simply add 1, enter 1, sorry, 0, exit. Don't forget to save the CTC variable content on the disk again, and then now you can generate a report and have a look if it increased or not. Seems to be better, isn't it? So I can prove it now. If I have a look here, this first pair, MCDC condition 1, this consists of test number 1 and number 4. There is a plus sign here and here, meaning it's successful. And you can see that actually, yes, it has been done successfully once. So if you want to increase towards 100% coverage, you may want to write test vectors over here to enter the right values in your console in order to increase this value. But I won't do it today. I will let you do this on your own if you want to test it, and please do so. For the second part of the demonstration, we use a different mechanism to get the mon.dap file. We won't use anymore the save command from the debugger because we assume the debugger is not available anymore for retrieving information from the target through the JTAG or whatever mechanism is available for debugging. Instead, we'll use a kind of console through, for instance, a serial line where you can collect information from your targets. So it means that you need to write a very small application to generate, to format on the output the content of CTC array down to this file through, for instance, a serial link. So it will be the purpose of next demonstration to see how we can add a file to generate Intel HEX file down to the disk, and then go to the classical report generation. Okay, so back to the IR embedded workbench project, and we will open also the console, the virtual console. Again, this console is communicating through the micro USB port, which is available on our explained mini board from Atmel, and this is just like a classical RS-232, but instead using the USART application from this board. So it's quite convenient and available on most target for debugging applications. So what we add to the previous project is a new file called debugger.c, and the goal of this file, as you will see, which is quite simple, is just to generate the content of the CTC array to the serial line, and to have this using the Intel HEX format in such a way that afterwards we'll be able to copy and paste the information here within the console to the disk, and then generate the report from the coverage analysis. You may also want to use another application here just to take directly the messages, so the Intel HEX formatted file, or not file, sorry, but stream to the disk. But here today we'll use a very simple application just to demonstrate how you can achieve this in a very simple way. So what we need to do now is to add, of course, this file within the project, and to include this calling somewhere where it's near the end of the execution, for instance, and also after you made your coverage analysis. So here in our example, we just take the opportunity to save all this information after we enter the 0 value in the console, which is the end of our program typically. So here we just send a message and the Intel HEX formatted stream. So this example is available, by the way, if you want to check it by yourself, and it's fully documented, and you will be able to adapt your own project based on this simple project. So what we can do now is just launch the modified project. So after the compile and link successful, we start debugging application, and again we'll have to press the go function. So same as previously, we are able now to enter some values, for instance 5, 9 and 0. And so what I've changed now is that we have generated this stream formatted for Intel HEX, and what we can do now is select the file content here, so Control C. So you may want to open an editor and then save the contents here. Okay, so you may want just to save over the existing mod DMP, which has been generated by CTC array macro, and the content won't be binary, but will be Intel HEX in this case. So okay, and now this is exactly the same process that we used previously. Now that we have this mon.dmp file on our disk in the working directory. Now we can generate the report. And this is exactly the same process when the file generated using the save command from the debugger, except here you have manually copy and paste the value down to the disk. And you should have some results which are similar to the one we got previously. And the same, we could improve the coverage and go back stepping within the process of improving our code coverage features. So this is the end of this demonstration, and this project is available if you want to check the integration. You need to have the IA embedded Workbench IDE and the evaluation board, which is a few dollars or euros only. It's very cheap boards to buy, and you may also want to use it in simulator mode if you don't have this target. So this is the end of our presentation and demonstration. Thank you for attending. If you are interested in getting more details, please visit our website, verifysat.com, where you can get all information about our products, technical description, brochures, papers, videos, and many more material. Feel free to ask us for free evaluation. Goodbye and thank you.